Hello, I wanted to record a video on a couple additional problems. One of these is I think, next to last or maybe last example on MO theory from the lecture notes from chapter 9. So this is looking at O2 with a minus charge. And so the idea here is if we have B2, C2, N2 are their ions, and we use the chart on this side, we have O2, F2, neon 2, or their ions, we use the chart on the right side. And the difference is really just this orbital energy here goes lower when we have O2, F2, neon 2. And we still have to think, and this might help, this might not help. You may or may not even have to do this to get the answer right, but this is just kind of looking at one of the atoms for O2, 2 minus. It's like picturing an oxygen atom, 2s2, 2p4 configurations O. Add one more electron in for one of them being O minus. It doesn't matter which one. You have this O minus versus O. And it doesn't even matter so much what you write in here, because it's really what you write in the middle for O2, 2 minus that really matters. So the MO diagram is trying to show us the relative energies that these orbitals have once they start overlapping with each other and making bonds. And so a bond goes down, so a sigma 2s, because it comes in the 2s orbitals, like we don't write a B, but we could write B for bonding or star for anti-bonding. So we just tend not to write the B there. So that's our bonding orbital. Gets 2 electrons. We got to put 6 plus 6 plus 1. We got to put 13 electrons in here for O2, 2 minus. So we put 2, 4, 6, 8, 10, 12, and then we pair one of them up for 13. Not asking this question, but this molecule would still be paramagnetic, would be pulled into a magnetic field. What else? So the question's asking for the bond order. So the bond order, let's cap off our orbital. Sigma star 2s is the next orbital up, 2 electrons. Sigma 2p, pi 2p, both of those are down relative to the orbitals they start with, so those are both bonding orbitals. And then we have the pi star 2p, and then the sigma star 2p is empty with no electrons. And so our bonding electrons are 2 plus 6. So these are our bonding electrons. So we have 8 bonding electrons. My anti-bonding electrons are just these 2 here, plus these 3. So that's 2, that's 5. Then my bond order is the number of pairs of electrons, so we got to cut this in half. So the bond order here will be 3 halves. So when we think of O2, we might have thought, whoops, if we were just doing a Lewis structure, by our Lewis structure rules, we would probably have started with maybe like O2, 2 minus, and then we kick an electron off. That doesn't matter because we're going to get the same Lewis structure. So we might end up with this Lewis structure here, or where the electron is over here. This structure, those are both equivalent Lewis structures, actually resonance structures of each other. And so that would be our Lewis structure as having something like this. But then what we see from the MO diagram is that maybe the bond order is better thought as looking like this. And then where's our other electrons? So our other electrons would be here and here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And so notice that in this structure here, these electrons are spin paired, and this one here is just paired in the same direction. I mean, I don't know if we really need to sketch this Lewis structure, but if we were trying to sketch a Lewis structure, I'm just trying to simply demonstrate that we have now 3 halves bonding electrons instead of just a single bond. So we get a little bit of a different Lewis structure for O2 with a minus, with the MO picture to show us a 3 halves bond order. And then if you look at each O, 1, 2, 3, 4, 5, 6, 7, 8, notice how each O is actually satisfying the octet rule with this Lewis structure, because each O has 8 electrons surrounding it. So a very interesting picture that we get from MO theory actually giving us a Lewis structure where it looks like each O has 8 electrons surrounding it, despite having an odd count of electrons. I had skipped this question in the notes because we had done a question like this on Monday where I was sketching out some structures. So this question here is asking us to consider Lewis structures, classify hybrid orbitals, give some approximate bond angles, and then sigma versus pi electrons. So the key on this structure is being able to kind of sketch our CH3 to C, double bond O, single bond O. Now you might be wondering, how do we know double bond here, single bond here? Well, that's because it gives each O 2 bonds and 2 lone pairs. So it gives oxygen the count it desires to keep a 0 formal charge in an octet. So oxygen versus, let's do it this way. Let's say carbon versus nitrogen versus oxygen versus fluorine in terms of the number of bonds versus the number of lone pairs that they tend to form to give them an octet versus a 0 formal charge. So this is lone pairs. So 4 bonds, no lone pairs for carbon. So like CH4. 3 bonds, 1 lone pair for nitrogen. So like NH3. Water, 2 bonds, 2 lone pairs. So like water, like this. And then fluorine, 1 bond, 3 lone pairs, like HF, like this. So we can take advantage of these basic ideas to sketch Lewis structures for organic molecules. So if we're counting and looking at our bond angles, these are closer to 109.5 because it's tetrahedral. That's sp3 for that carbon. This carbon here, trigonal planar, 120-degree bond angles about it, more like sp2 hybridization. Again, we can predict slightly greater than 120 for the double bond, single bond angle. Water, the oxygen sp3 tetrahedral, 4 domains, so closer to 109.5, and the lone pairs compressing that a little bit. CH2, CH, C, CH, so H to C to H to C to another C to an H, so I need a double bond here between these 2 carbons, and then I go to, I'm going to do it here, I don't have enough room to write it up for what's in the way. And then I go to another C to another H, so I'm going to go triple bond to go 4 bonds. And so we go SP here, SP2, whoops, I don't know why I always go SP2, I always like write the 2. So SP2 here, and so about 120 here, 180 here, and then we didn't count sigma and pi for the previous example, I'll do that in a minute, but sigma here, go 1, 2, 3, 4, 5, 6 sigma, and then 1 pi, and then 2 pi. For the triple, so I get a total of 6 sigma plus 3 pi bonds. And so the double bond is a sigma plus a pi, and the triple is a sigma plus 2 pi. Now let's go count sigma and pi for this structure up here. So we got 1, 2, 3, 4, 5, 6, 7 sigma, and then 1 pi. The 1 pi being this second bond here. So again, most double bonds, sigma and a pi, triple bond, sigma and 2 pi. CH3CN, so CH3 to C to N. We could do this and then just make our triple bond here to lose those lone pairs to give carbon 4 bonds, nitrogen 3. Get there a few different ways, but this is going to be 180 degrees here and then 109.5 degrees here. So sp3 and then sp for the C and N and the CN group. And then we have, in terms of sigma versus pi, we have 1, 2, 3, 4, 5 sigmas, and then we have 2 pi's. Get that. So I wanted to pull a couple different questions on MO theory. Which molecule is diamagnetic? So diamagnetism is 0 unpaired electrons. Paramagnetic is 1 or more. And so B2, C2, And then O2, let's do O2 first. We know O2 is paramagnetic, but O2, we're putting 6 plus 6 for 12 electrons in for O2. So 2, 4, 6, 8, 10, 12. So definitely paramagnetic for oxygen. If we do B2 next, so B2, 3 plus 3, so 6 valence electrons. So we put 6 electrons in for boron, and it goes paramagnetic as well. And then we go to C2, we put 2 more electrons in, and they spin pair, and then we go to have 0 unpaired electrons. So C2 would be diamagnetic, the other 2 paramagnetic. And let's look at one more question for today. Let's rank some bond lengths, C2, O2, F2, B2. And so let's go back to B2. So we had 6 electrons in for B2. So B2 has a single bond where we have a really kind of strange structure where we have, for boron, we'd have sort of a bond here for our sigma 2s, and we'd have our sigma 2s antibonding orbital putting electrons out here in the molecule. So we'd have, like sometimes we think of these diagrams and the orbitals, as being separate orbitals. Think about them simultaneously. And then we'd have 1 electron in this pi bond here. Then we'd have another electron in the pi bond sticking straight out of the page. So we have electrons kind of all over the place for B2, but the net bond order is just 1. So the bond order of B2 would be equal to a half 4 bonding electrons, so these 4 electrons here, minus these 2 anti-bonding electrons. And so that's going to equal a bond order of 1 for a single bond. Let's actually do one let's do F2 next, because I know F2 has a single bond. We're thinking, from a Lewis structure, it looks something kind of like this. We can reinforce this Lewis structure when we put 14 electrons in, 7 times 2, so 2, 4, 6, 8, 10, 12, and then 14. And then our anti-bonding electrons are these 2 here. So this is sigma star 2s. This is the pi star 2p. These are the only star electrons. So our F2 bond order from the MO diagram would be 8 bonding electrons, 6 anti-bonding. So 8 bonding minus 6 anti-bonding gives us a net bond order of 1 for a single bond. So if I'm looking at F2 having a bond order also of 1, single bond's longer than double and triple, we probably know oxygen is going to be a double bond. So O2 and C2 are going to be shorter than F2 and B2, but fluorine as an atom is smaller than boron as an atom from our left to right trend. So from our left to right trend, fluorine's smaller, boron's bigger. They're both single bonds. So whenever I'm comparing 2 bonds of the same type, I just compare the atomic radii trends and reason out that if boron's bigger, then boron is a single bonded, as a B2 bond is going to be longer than 2 fluorines as single bonds with smaller atoms making up that bond. So my B2 bond length is going to be greater than F2 in terms of my distance, just because fluorine's smaller than boron, and they both form the same type of bond. Then for O2, I go to 12 electrons, use this diagram over here. So if I kick these 2 electrons out for O2, I then only have 4 anti-bonding electrons, so my bond order for oxygen is going to look like a half. And then 8 minus 4 for 2 for a double bond, as we would expect. So our Lewis structure like this, and then just something peculiar with the spin of our electrons such that we pick up that paramagnetism. But then double bond for O2 is going to make it shorter than F2. So O2 being double makes it shorter than F2 being single. And so this just goes to, single bonds longer than double, longer than triple. And so the double bonded O2 is going to be shorter than the single bonded F2, despite the fact fluorine as a single atom would be smaller than oxygen as an atom. So despite oxygen as an atom being bigger, the double bond, those extra bonding electrons pull that bond length in shorter. And then lastly, we can compare well, actually, sorry. I thought we were going to compare N2, but it's not N2, it's C2. I was going to say if the other molecule we were comparing was N2, then N2 being triple would be the shortest. So if we were going to N2 next, it would be shorter. But what about C2 being double? And so C2 is a double bond. How do we get to double? Well, we got to put 8 electrons in, so we put 2 more in. So our bond order for C2 is a half. Then we have 6 bonding electrons, only 2 anti-bonding for a bond order of 2. And then carbon is bigger than oxygen, just from left to right. So if we're comparing C2 versus O2, the carbon being bigger makes C2 longer than O2. So the same type, we're comparing atomic radii sizes. And then being double makes C2 still shorter than F2. And then C2 is going to be longer than O2, again, because C is bigger than O, and these are both double. These are both single, and B is bigger than F, hence our trends. Okay, so the right answer to this question should be, what was it asking? Which one's the longest? So the question's asking for the longest bond should be B2. So the longest bond here should be B2. Okay, and I want to go back and look at one more chart. So let's look at this chart here. What I wanted to compare is on this chart, you can actually compare that trend where before in the previous slide we had B2 longer than F2, longer than C2, longer than O2. And then if we wanted to throw nitrogen into here, it wasn't on that group, it would be even shorter due to being triple. And we can kind of compare, because this chart here is actually showing us these bond lengths. So let's see if we're right. So B2, 1.59 angstrom. F2 should be shorter, 1.43 angstrom. So that's good. And then C2 was 1.31 angstrom. So that it's, shorter as we predict, but then it should be longer than O2. O2's bond length, 1.21 angstrom. And then if we throw nitrogen onto the list, N2, even shorter, being triple, 1.10 angstrom. So you can kind of see like all of our sizes make sense, from the bonding type that we get for triple versus double versus single, and then even the 2 singles, the bigger atom being longer, and then the 2 doubles, the bigger atom being longer as well. Okay, so I just thought I'd do a little bit of an extra video for some MO questions to hopefully give you guys some good preparation in the weekend if you're preparing for midterm 3. That's next Wednesday night. All right, guys, have a great day off of Electron Friday and a great weekend, and I'll see you next week.